Welcome back to the second lecture of engineering mechanics. Let's learn together. So, today we are going to see the idealization of a rigid body as a particle. This image is already familiar to you. Two tugboats are pulling a barge, and if you see, the barge is idealized as a particle. The forces acting on the barge due to the tugboats are represented as tension forces T1 and T2. If you observe carefully, these two tension forces are applied at the same point, and the resultant force, that is the 5000 newtons, is also in the straight line. So, this implies that if you want to idealize any rigid body as a particle, all the forces should be acting at the same point, or rather it should be concurrent forces. If you see the image in the right hand side, there is a hook, and that hook has two forces P and Q acting on it. And here also we can say that both the forces are concurrent. So, that means if a rigid body has to be idealized as a particle, we must be sure that all the forces are acting at the same point. So, let us say forces in a plane. A force represents the action of one body on another and is generally characterized by its point of application, its magnitude and its direction. Now, magnitude of a force is characterized by a certain number of units, whereas the direction is a combination of line of action and sense of the force. Now, experimental evidences show that you can add two forces which are acting at the same point. So, in this case, at point A you have two forces P and Q, and if you see, point A has both these forces tail. Here you can see the force P, and if I keep the same length line at the head of Q, and same way the same length line Q at the head of P, it forms a parallelogram. And when we have such a parallelogram, the diagonal, which consists of both the tails and both the heads, if you see here, it will be a head and a tail, here it will be a head and a tail, but here it will be both tail and here it will be both heads. So, if you consider this diagonal, that is the one which goes all the way from the tails to the heads, that forms the final resultant force. And this law is completely based on experimental validation, and it does not have any mathematical derivation. So, we are defining forces as vectors. So, what is a vector? A vector is defined as a mathematical expression possessing magnitude and direction, which add according to the parallelogram law. So, fixed vectors are there and free vectors are there, and there are equal vectors and negative vectors. So, here in this case, these are equal vectors and these are equal but negative vector. Now, coming to the fixed and free vector, fixed vector means it has a point of application, whereas free vector is free to move anywhere in a plane of action. Now, coming to the addition of forces. The sum of the two forces P and Q are obtained by attaching the two vectors at the same point A and constructing a parallelogram using P and Q as the two sides of the parallelogram. The diagonal that passes through A represents the sum of the vectors P and Q. P plus Q is also equal to Q plus P, and that is evident in triangle law of vector addition. The sum of the vectors, from you just have to keep the tail of one vector on the head of the other vector. So, in this case, from A the vector P is going this way, and on the head of vector P you keep the vector Q. This will be the resultant. And if you want to add first Q and then add P, it will remain the same. So P plus Q is always equal to Q plus P. But then what about vector subtraction? There is no vector subtraction as it is. There is only vector addition, and you are just going to add a negative vector to another vector, which will result in a similar way. So here I want to negate this Q vector from the P vector. So P minus Q. Q was in this direction, but P is going to be in the other direction. So P minus Q will be another vector. Now, if I have 3 or more vectors or 3 or more forces acting on the same point, how can I go about it? I can always use a cumulative addition method. That means I add P and Q, I have the P plus Q as a resultant vector, and again the resultant vector plus the S vector will give me P plus Q plus S. Same, it is otherwise known as quadrilateral rule. That means if you have n number of vectors, you keep all these vectors with one of the tail of the vector on the head of another vector, like in this case from A, P, Q, S, or here say in this case S, Q, P. Finally, it all adds up to the same resultant vector. So it is a cumulative sum. So this is a typical example of the quadrilateral rule. That means you have multiple forces acting at the same point A. So P, Q, S, the resultant vector will be from the tail of the starting vector to the head of the ending vector. So here I have added P plus Q plus S. So from A to the head of S. Now, resolution of force into components. You have one vector, you can divide it into two vectors. So if you follow the same order here, I have a force which is represented by this P and Q. So the sum of P and Q will give me a force vector F. So a single force F acting on a particle may be replaced by two or more forces, okay, which together have the same effect on the particle. The same force F can be represented with a set of another two vectors P and Q as shown in figure B. Okay, so these forces are called the components of the original force F, and the process of substituting them for F is called resolving the force F into components. Okay, so now let us come to a simple problem here. So on this bolt I have two forces P and Q acting. So if you see here carefully, I have the angle between these two vectors. So how to find the resultant of these two vectors mathematically? Okay, so mathematically we can say the solution is r square is equal to p square plus q square minus 2pq cos theta. So with that we can find out what is the resultant magnitude, and there is a graphical solution to it, and the graphical solution is as similar as what we have seen in these cases. You are just going to add one force on the other force, and then the resultant will be available. So in a graphical method, what you have to be careful is that you have to draw each vector to a particular scale. In this question here, I have q is equal to 60 Newton. So I have to represent this vector q with a proper scale. Say for example, let me take 10 Newton is equal to 1 centimeter. So in this case, vector q can be represented as 6 centimeter long line at an angle of 45 degrees, and on the head of q I place the vector p, and that p is going to be 4 centimeter long line. So my resultant would be the line which joins from this point A to the head of the vector p, and we can measure that and also measure the angle associated with it. So that's it for the second lecture. We will meet again in the next lecture. Thank you.